swap. So my talk today is going to be probably a little bit less technical than what we've seen so far. And what I want to do is I want to show you that matrix product states can have really probably potentially useful applications in areas related to computational fluid dynamics. And of course, this is an area where you're dealing with classical physics, in particular with classical turbulence. And that's, of course, one of the areas which are unsolved up to this point. So this is basically something that isn't really fully understood. And if there was a question yesterday, tell me a field where you don't know answers to 2 digits, then that's turbulence. I'll show you some plots in a couple of minutes where I think it's things I know maybe to 1 digit. And of course, this has a huge impact on what we can do and what we how we use energy. And I've got a couple of examples here which all show kind of small changes to aerodynamic designs that make about a 10% difference in how much energy is used by these types of, in this case, vehicles to actually move forward. So for instance, there are counterintuitive designs shown here for these kind of cars that have edges rather than rounded off corners. And it turns out that edges, in this case, reduce the drag of a car, which is kind of counterintuitive. You wouldn't expect that to happen, but instead of kind of rounding off edges, if you make them a bit more edgy, then it can happen that you reduce drag and thus reduce fuel consumption. If, like me, you're kind of living in a place where there are lots of ships going by, you see that empty kind of vessels can often have, and most of them have, these so-called bulbous bows, which basically are big blobs in the front of a ship. And initially you might wonder, what is this good for? This actually produces a lot of extra drag. But in fact, it's not like that. This is basically reducing the amount of waves that go around the ship and make the ship consume about 10% less fuel than it would otherwise. And it's not something that has been worked out through computational fluid dynamics, but rather looking at dolphins and their noses and basically matching how their noses look like. They thought, well, let's put this thing there, it might help, and it does. If you, sorry. So, oops, I didn't want to do this. If you look at, for instance, cars, and in particular racing cars, in the 1970s, and a Formula One driver called Gurney invented this kind of so-called Gurney flap, which is basically just taking a wing of a car and putting a little kink in there. It turns out that this kink increases the drag of these wings on a car quite significantly. And these days, you find these kind of Gurney flaps everywhere, even on all these kind of big wind turbines. There are all these little flaps on them, and they basically improve the efficiency of these wind turbines significantly, again, by something on the order of 10%, although it's really just a kind of tiny flap that you have there. And around this tiny flap, vortices form, and those vortices around these tiny flaps will actually improve efficiency. And similarly, if you have been flying around for long enough, like started in the 90s or so, back then airplane wings were straight, and they ended straight. And suddenly in the 90s, they started to be bent up, more and more of them. And these days, they all look like this. And again, the reason is that if you put these kind of winglets at the end of the wings, additional vortices form, and the airplanes use significantly less petrol. So all of these kind of changes are changes that are worth multi-billions of dollars. And they're all basically related to understanding how turbulence works. And for that reason, institutions like NASA have a huge interest and huge research programs on how to improve our understanding of these kind of turbulent flows and how to do better computational fluid dynamics. And what I show here is the kind of master plan that NASA has produced on what they want to achieve by 2030. And there are all of these kind of different techniques that they are trying to develop, from kind of red, meaning doesn't work, to yellow, and green then, meaning does it works. I'm not going to go through all of that, but I'm going to kind of look at here. They have an explicit part in here that looks at CFD on revolutionary systems, and among them is quantum computers. And in particular, they hope that there will be some kind of decision points here in 2025 to 2023 to 2030, where actually such unusual architectures might be helpful and might become useful for computational fluid dynamics. But of course, these guys are scientists themselves. They are aware that you can do calculations on a quantum computer, some of them more efficiently, but they also say this doesn't mean it's necessarily faster than a classical computer. So it's kind of a bit less enthusiastic maybe than some investors are at the moment, which probably is a good thing. Okay, so what I want to show today is that basically we can try to use matrix product states to solve problems related to computational fluid dynamics. And I will stick with what is possibly the simplest example that you can think of. And this is just the Navier-Stokes equation in 2 and 3 dimensions in the incompressible limit. So here we basically have an incompressible flow where the divergence of the flow field is 0. And here the Navier-Stokes equation with this term here containing the Reynolds number as the only free parameter. The larger the Reynolds number, the more likely a flow is going to be turbulent. For small Reynolds numbers, simulations are pretty simple. It's like steering honey. But for large Reynolds numbers, this becomes more difficult. And if you look at possible applications of just having better solutions to this type of equation, you can see that here we don't really know the answer to what the solution to this is. This is, for instance, used for weather forecast. We certainly can't claim that we know this to any digits, how the weather becomes the next day. And in 3D, you have aerodynamics, combustion physics, and so on and so forth. So all kind of big and important topics. And the first challenge that I would like to discuss in solving these types of problems is related to the length scales that you have to cover. So if you look at these types of equations and you ask what is the kind of grid that I need, then it turns out that there are 2 length scales that are relevant here. One is the length scale L, that's the length scale basically of the whole system that you want to analyze. And the other one is the so-called Kolmogorov length scale eta, and that's the length scale at which eddies are dissipated into heat. So imagine that you bring kind of energy into this system on the length scale of, for instance, a submarine or an airplane or something like this. And then what happens is that these different flows, or this energy that's brought into the system, gets dissipated to smaller, gets kind of turned into smaller and smaller vertices on smaller length scales. And at the Kolmogorov length scale, it gets dissipated into heat. And if you want to describe this system, you have to describe all the length scales from the big length scale L, size of the system, down to the Kolmogorov length scale. And the kind of Reynolds number determines the ratio between those 2 length scales, L and eta. And now if you look at some of the interesting examples that one wants to study, then what we see here is that, of course, insects might be still pretty easy with 1,000 to 10,000. But if you go up to aeroplanes, you have Reynolds numbers that are on the order of 10 to the 7. Even if you take these little kind of drones, you have already Reynolds numbers of 10 to the 5. So if you want to do a 3-dimensional simulation of that, you need to take 10 to the 5 to the power of 3. So 10 to the 15 grid points, and that starts to become challenging on classical computers. If you want to do this for Boeing 747, you'd have Reynolds numbers of 10 to the 7 to the power of 3, so 10 to the 21. That's a bit too much for current computers. That's why they're going to these exascale computers, and that's why you need such big computers. It gets even worse if you look, for instance, at submarines. They have Reynolds numbers of 10 to the 9, and I didn't really know how to work out the Reynolds number of the atmosphere, but that's pretty huge. So basically what you have is you have a large number of problems where you need very fine grids and need to cover long length scales to do any sensible numerical calculation. And if you also look at what is known here, so this is from a paper from 2017, this is basically the blue part here, shows what is the kind of sectional lift to drag ratio, and the ratio of which this goes is pretty large still, so it's not so easy to work out. Yes?
Solve it numerically, like at this scale, is the problem actually the numerics, or we don't actually know the equations of state accurately enough, or there's corrections to the Navier-Stokes equation, etc. Like, how relevant is it to exactly solve the Navier-Stokes equation to a submarine?
Yeah, this of course is exactly the same question you could ask on any of the models that we use in quantum physics. I would say that in this particular case, the kind of corrections will certainly be there. For instance, it will not be incompressible. You will need to take into account the compressibility. You will need to take into account the thermodynamics of the problem. But that's extensions that you know how to do. I mean, you know in principle how to add energy dissipation, heating of the air, and so on. There are much more complicated models than I have written up here. The question is, how much more difficult will the computations become when you do this with matrix product states? I hope it's manageable, but that's something that people are working on. I'll say a little bit more about this a bit later. But yes, it's an absolutely valid question. This model is only of limited validity. Okay, but it's already challenging enough. So basically, when we look at this, what I said before in a bit more detail, how does the energy flow in these types of systems? And I'm going to explain this because it will show up very soon again in the matrix product solutions that we have. So if you basically have a flow in 3D that is turbulent, what happens is that on some length scales, energy will be injected, and then basically this energy will lead to large vortices as shown here. And these vortices will couple to smaller vortices, will couple to smaller vortices, and smaller and smaller and smaller, until you reach this kind of Kolmogorov length scale where they dissipate into heat. And of course, I said this now in a kind of very blunt way, but Richardson in 1922 was still a bit more of a poet than I am. And so what he basically said and defined this whole field was big whirls have little whirls, which feed on their velocity, and little whirls have lesser whirls, and so on to viscosity. So this is kind of a nice poem that you can make on these types of problems. So that's what happens in 3D. And basically what then follows from this is this Kolmogorov energy cascade, where basically you have energy inserted here at a long length scale, and that energy then travels down, so the vortices become smaller and smaller and smaller, and then dissipate. The situation in 2 dimensions is different. In 2 dimensions, if you actually insert energy at a certain length scale, the energy will move to longer length scales, and the so-called entropy will move to shorter length scales. So basically you have energy flow one way and vorticity flow the other way. I'll give you a kind of definition of the entropy on the next slide, so because it will appear later again. So basically the situation here is different. And of course, the fact that the energy here flows to longer length scales is the reason that tornadoes and thunderstorms and so on can form. Otherwise, they would just all kind of collapse and never really kind of be able to grow. Okay, what is this entropy? Well, basically, entropy is a measure of how much vorticity you have. So the entropy can be written in general as the integral over the whole volume of the flow of this nabla times v modulus squared, where this has a bit of an unusual definition. So note I wasn't just sloppy and forgot the dot here. This is not a scalar product, but this is a product that's written here. And if you have now an incompressible flow that has zero divergence, then you can basically rewrite this entropy as the integral over the vorticity modulus squared. So this entropy is hence a measure of how much vorticity you have in the system. And importantly, if we have the Navier-Stokes equation, an incompressible flow, as we will have, this entropy multiplied by the viscosity is equal to the loss of energy. So you can basically work out this entropy, work out how much energy you lose, and if you compare the two and they are the same, you know you have, at least you have a test for how good your simulation, how good your solutions are. So that's what we are going to use this entropy for. So what I want to do now is, I want to basically, after this kind of introduction, show you that matrix product states are a good way to encode such fluid flows, and that they can be that they have properties that are very well adapted to these properties of fluid flows that I just explained to you. Then I will work out and show you classical entanglement spectra and turbulence correlations, and I will do all of that based on solutions that were obtained numerically by standard so-called direct numerical simulations, so numerically accurate solutions to the Navier-Stokes equation. I just take those in a similar way to what we heard in the previous talks. I will take those solutions, write them as matrix product states, and then we'll analyze their properties. And then I will actually, from the results that we there get, we are encouraged to use a matrix product algorithm to evolve those, and I will show you a few examples of what we get with matrix product algorithms for various different paradigm examples like jet formation, Taylor-Green vortices, and driven cavities. And in the end of my talk, if I've still got some time, I would then actually also like a little bit to discuss how these kind of ideas can be helpful for developing algorithms on quantum computers that solve these types of computational fluid dynamics and basically do some what we call quantum computational fluid dynamics. So this is actually going to be trivial for you. I produced these slides for engineers who I'd like to explain what a matrix product state is in real space. So I'm going to go very quickly through this. You will all find this, I think, pretty easy. So what we do if we have a grid, like here, this two-dimensional grid, and we want to represent the flow field on this two-dimensional grid, what I do is I pick out the largest length scales, and I pick out the 4 grid points here, this lower grid point here that would describe this part of the grid, this grid point here would describe this part, and so on. And then I take the fluid field U of RQ, and write this in a Schmidt decomposition as a function on just these 4 red dots times functions on all these other dots here. And if you do a Schmidt decomposition of the flow field that you have, then basically in this first step you can get a maximum Schmidt number of 4, and you will have kind of 4 functions here that represent the longest length scale of your fluid flow. Then what I do is I take these functions and encode them into 2 qubits. So I'll take 4 2-qubit states, and I just encode this function capital R into these 4 qubits. And so this kind of first pair of qubits will hence contain functions that describe my fluid flow on the longest length scales that the system contains. So it will basically give you a very coarse-grained description of the fluid. And then, of course, I have this Schmidt decomposition here of this function, equivalent to a Schmidt decomposition of a corresponding wave function, with these first couple of qubits being separated off. And then I just repeat this step. I take each of these red dots and the corresponding subgrid, and again divide it into 4 subgrids. I do this for all the different subgrids, and I do another Schmidt decomposition. So I do exactly the same thing as what we usually do for spin systems. But the important difference is I do not go spin by spin. I do not walk along space. But what I do is I walk along length scales. So there is no such thing as a 3-dimensional or 2-dimensional or 1-dimensional system. Length scales are by definition always 1-dimensional. So I have certain distances between the different parts, and length scales therefore always have just one spatial dimension in a sense. And this procedure is continued. So basically I chop off individual parts of the lattice and develop a matrix product description of the fluid flow by always kind of pairs of qubits describing certain length scales. Yes?
So I need to verify that. You mentioned you have just the 4 points there.
Yes?
So how do you get them to this Schmidt decomposition?
Oops.
Do you have to complete the function?
Yeah, imagine that I have the function.
Yes.
So I will have the function from some numerically exact simulation. I have this function, and I just take this function and do a Schmidt decomposition, just like you would do for a quantum wave function. And just SVD it, basically, with these 4 grid points taken out. So I do nothing fancy for you guys. And this is pretty much the same as we'd always do. The only difference is it relates to a different physical quantity. Yes?
I understand this in this way. So this is some sort that you are training a neural network.
Can you just see mine, please?
Can I understand it in this way? Yes, you are fitting it to something that like a neural network. Then the input is the binary of the coordinate, each digit of the binary coordinate, and the output is the velocity.
I mean, I wouldn't see it as a neural network. Usually they have a kind of more specific structure than what we have here. It's really just a kind of a matrix. I mean, it's just expanding the fluid field into a matrix product state. So just like you do in DMRG, DEBD or so, but with a different physical meaning.
Yeah.
Okay, so and that's the procedure that we're going to follow. And now, of course, what I do is I look at how much entanglement, and entanglement is under quote here, entanglement basically gives us the correlations between the different length scales. do I need to represent a solution to the Navier-Stokes equation? And I show here two different examples. The first example here is a two-dimensional simulation of a so-called developing jet. So that's basically the air that comes out of a jet engine. And what you see here is that if you look at the various different partitions in the grid, so basically these are this kind of first step, second step, third step, and so on in this series of length scales that I did before. And here I have the bond dimension chi, where basically this bond dimension tells us how much entanglement or how much correlation is there between the long length scale and the shorter length scales here. And I look at the bond dimension I need to faithfully represent this kind of fluid flow. What I find is that this fluid flow is pretty low in bond dimension. So I can chop off this whole top of this pyramid without any substantial loss of accuracy. So in particular, the blue line that you show here is basically chopping off a large fraction of the possible space that you might need, and still leads to a loss of accuracy of just 1%. And the important thing to notice, this is on a kind of logarithmic scale. So this top of the pyramid is much, much larger than it looks like here. This is really exponentially larger than what you see at the bottom. And if we do the same thing for 3D, well, the situation is not quite as nice as in 2D, but this kind of 3D Taylor-Green vortex also allows us to chop off a significant part of the various different correlations that might be there. And again, since this is a kind of exponential scale, this top of the pyramid is actually much larger than it would seem. Okay, yes?
Per scale?
Yes. So we use, I mean, in this particular case, we can do other things as well, but in this case, we do 3 qubits per length scale and basically divide things into octants. Okay, and so we can look at these entanglement spectra, or this kind of, in a bit more detail. So basically here you see where we cut them off across this kind of dashed line. There are some kind of more terms that we have down here, but the dominant terms are really the red ones here. Those are the ones we keep. And as time develops, of course, a little bit more of this entanglement develops, but it stays always pretty small. It can always be truncated very well. And now we look at the entanglement entropy of these two different flows. And what we now find is very much in line with what I explained before, namely that in 2D, energy flows towards the larger length scales, and in 3D, it flows towards the shorter length scales. So if we look at the 2D situation, there is this solution here. The green solution is a flow field, and its entanglement entropy across the various different partitions. So basically, the values down here give us indication of how much correlation or how much is going on at very small length scales, and here is a very long length scales. So initially, we have this solid curve here. As time increases, these curves move towards longer length scales, indicating that the flow really kind of the eddies or the kind of structure moves towards longer length scales. If we do the same for the 3D flow, the exactly opposite happens. We start out here at relatively longer length scales, and the curve shifts towards the right, indicating that structure of the flow moves towards shorter length scales. So this is exactly in agreement with these kind of two different types of energy cascades that I showed before that are known to exist in these types of flows. And we can see them here from the entanglement entropy. So this is all very encouraging. So basically we have got these properties of this kind of poem on whirls and how they connect that basically tells us that these fluid flows should not really have very strong correlations between the longest and the shortest length scales, because these eddies don't interact directly with one another, but they always interact in a cascade. So we get large eddies interact with the next smaller, next smaller, next smaller eddies. And so that means there shouldn't really be direct correlations or direct interactions, if you wish, between very large and very small eddies. Okay, and that, of course, is very good for matrix product decomposition, because that means that we expect a small bond dimension, and that's what we've seen when we did this numerically. And we also see that this entanglement spectra, or the entanglement entropy, now, of course, have nothing to do with entropy, but can be used to understand quite a bit about the nature of this flow. And we've just scratched the surface here. I believe that a lot more can be done on this. So what we want to do now is we want to actually develop an algorithm for solving this Navier-Stokes equation, staying always in the matrix product description and never having to blow this thing up into its full description. And since it's the last session of the meeting and it's Friday evening, I've decided to not give you too many technical slides, so I will just have 1 or 2 in there. And this is the one that I want to show. And then I'll show you pretty pictures again, I promise. So basically, the way we do this problem is we define a cost function that we want to optimize. And this cost function has 2 parts. The first part here of the cost function has a Lagrange multiplier mu here in front. This part of the cost function, that ensures incompressibility. So we make this prefactor mu large enough. And if the prefactor mu is large enough, the solution will always have a divergence that is close enough to 0. This is possible in this particular case. In other examples that we did, you can't do it that easily. We did different methods. But this is one way to actually ensure incompressibility. And then this last part here is just the cost function that needs to be minimized when doing an Euler step forward in time by some time step delta t, where the previous flow field is v, so velocity field v, and the new one is v star. And so what we need to do is we need to minimize this cost function for a given v that we have from the previous time step. And now, of course, if you look at this, this is just quadratic in v star. So this is a relatively simple optimization problem. In particular, we now write this velocity field in its components and write every component as a vector, and we can rewrite the cost function as shown here. And then we can turn this into a linear optimization problem, and then we do DMRG to solve it. Okay, so I'm not going to go through any of that. This is kind of just more or less standard. And here's what we get. So basically here, I show this kind of jet formation where we have here, this is the vorticity shown here, where we have a flow field that emerges from some kind of nozzle out of a jet engine, for instance. And what we get here are vortices flowing either left or right-handed. And this is how this develops over time. So this is basically at starting point time 0, and then how this develops over time. And yeah? Compared to what?
Compared to the real space methods.
I'll come to that in a minute because this depends mainly on how the chi goes with the Reynolds number. Okay, I have a couple of plots that will show that. You can get an exponential speed up, so the answer will be yes, here we get an exponential speed up. In the 3D case, we don't. But it's for the specific example, it's example dependent. So basically what we now do is we have here this numerically exact solution, and here we have solutions with various different chi's. And now you can look at them and actually do a visual comparison, and you will see that the solutions with chi equal 118 and chi equals 74 are pretty good. They are visually almost indistinguishable from what the direct numerical simulation does. Now, of course, this is a turbulent flow. So what I show here are ensemble averaged results, because of course every run of the numerical experiment gives you something different. It's too turbulent to just use one run, so one needs to ensemble average. Now in contrast, what we can do is we can of course do the kind of direct numerical simulation, but with an under-resolved grid, so-called URNDS. And if you look here at this plot, what that means is that I, instead of cutting my space of functions that I allow like this by cutting off the top of the pyramid, I cut the pyramid this way, okay? And you can see the significant amount of function that I will cut off that way. But this under-resolved DNS is something that people, of course, do because you can't have fine enough grids. It shouldn't be very good, as one can see from this initial plot, and that's indeed what we find. So if you do under-resolved DNS, you see that even at a grid that is roughly the same kind of computational complexity as this computation with 118 here, you get some visible qualitative differences compared to the other one. And if you make the grid smaller, it completely falls apart. So we do get here, in this case, with this choice of chi equal to 74, we get a reduction in memory requirements that is approximately a factor of 16 to 1 compared to the direct numerical simulation. And now, of course, yes?
Question here. Can you generalize it to more complex geometries like an airplane wing, in particular with boundary conditions not on a box boundaries?
Not on the box boundary. Yes, I can, but I haven't. Yes, but we have only done box boundaries. Yes, but yes, we can do this, and that's something we are doing at the moment. I'm going to, if I have time, very briefly explain it. But yeah. So basically, this is a saving in memory, and in this particular case, it will also result in a saving in the runtime that we have. But of course, if you look at the computations in this area, savings in memory and savings in runtime are both relevant. Okay, so it's not that you just need a saving in runtime. You really want an algorithm that has a high so-called arithmetic load, basically meaning that it does work hard on the data that is provided, and it doesn't spend all of its time shuffling data back and forth. As we've analyzed these algorithms for that, and they are pretty good. So they basically provide us for hardware architectures that are around with a pretty good load of the CPU and of the memory channels and so on. They are pretty good, well balanced. But the main thing here is really this compression of the amount of memory that is needed. And here is this kind of 3D example that we have. This is a so-called Taylor-Green vortex that decays into some kind of turbulent structures. And again, I show the same thing. Here is the kind of numerically exact solution. Here are solutions with various different chi's, and the corresponding under-resolved solutions are here. And again, you can see that the MPS approach is pretty good down to maybe a chi of 128. Then it becomes a little bit less good, whereas the correspondingly sized under-resolved simulations pretty much disagree with the direct numerical solutions pretty quickly. Okay, and in that particular case, we get a compression of 1 to 50, so we only need about 2% of the memory that would be needed for the direct numerical simulations. It's a huge saving on memory that we get here. Now I come back to this point that I made at the very beginning on the entropy. So the entropy in these calculations must be equal to the loss of energy in this system, so the amount of dissipated energy. And so we've measured that. And what we see here is that this works pretty well. So these kind of curves here show the results for the direct numerical simulation compared to the MPS calculations, and compared up here to the under-resolved simulations. And you see that the matrix product simulations are much, much better on maintaining this kind of quality criterion, on actually having agreement between the entropy and the lost energy. Okay, but that was just briefly. So now I come back to this question of what we gain in this in terms of runtime. So what we did is we looked at how does the bond dimension that you need in order to describe these flows increase with the Reynolds number. So of course, ideally, you want the Reynolds number to not increase as the bond dimension to not increase with the Reynolds number, which is maybe a bit too optimistic, but that's what you would like to have. And basically what we find is that in this 2D example that I've shown before, the Reynolds number first increases and then essentially stays constant. So this really does seem to saturate. Whereas in the 3D case, it does go up, and it does go up with a Reynolds number proportional to Reynolds number to the power of 0.71. So if we now turn this into runtime, so the runtime of our algorithm is chi to the 4. And chi to the 4, if chi scales like this, what we find, of course, is that in 2D, we get, with the constant chi eventually, we get an exponential speed up over the usual DNS, because the runtime doesn't increase anymore with increasing Reynolds number. In 3 spatial dimensions, we have in total a kind of scaling that is approximately the same. It's a bit worse in this particular case than direct numerical simulations, but of course it still has this advantage of saving a lot of memory and having a huge arithmetic load. Okay, so that we can analyze this, and we can look at all of these examples. How does the chi go, and then look at the scaling that we get. So now I come to this point of, can we do boundary conditions? Yes, we can do the boundary conditions. So in order to do boundary conditions, all that we have to do is we have to modify the matrix product operators that describe, for instance, our potentials or our Laplace operators to kind of have boundaries in themselves. And so when we do that, then we basically have boundary conditions encoded into the matrix product operators that are applied to these flow fields that I had shown before. And now that is most easily done, of course, for rectangular boundary conditions. But of course, nobody stops us from taking this matrix product operator then and transforming it via transformation of the coordinate system into any curvilinear coordinate system that we like. And in principle, we always get a kind of, so far, pretty well-behaved matrix product operator that we can use to apply there. And so one example that we did to demonstrate that this works is shown here. So basically, what we do is we have a lid. So this is just a box. It should indicate a box with a lid on top that is moving. And so as the lid is moving, the flow inside the cavity, inside this box, will start to flow. And here in this area here, a vertex will form, a large vertex will form, and that vertex then will eventually kind of decay into some kind of turbulent structure. And in this particular case now, because we do have boundary conditions, the kind of penalty method that I mentioned before with this Lagrange multiplier is not that good anymore. So what we use instead is a so-called two-step predictor corrector McCormick scheme that comes out of the fluid dynamics world, which is very accurate there. And I just bring this up because I would like to show that where the kind of bottleneck in these computations is then. What we do here is we basically take precisely a standard classical CFD method and apply that CFD method step by step in matrix product operator formalism and matrix product state formalism. So the only things we need to do is we need to add two states, we need to multiply, we need to solve a Poisson equation, and we need to do matrix vector or multiplication. All of this has been studied in the literature, and we can just use the kind of the existing algorithms for that. The main bottleneck here is the multiplication, because we do have a nonlinear problem now. We need to multiply different flow fields together in stepping the system forward. And this multiplication of two matrix product states goes like chi to the 4, and that's what is really the main limitation. If that could be made faster, then this algorithm would outperform anything that is classically available, but this one holds us back. Okay, I'm not going to go into too much detail. I don't have that much time left, so let me just continue. This is what these kind of vortices look like once they are fully developed. And basically, our results agree absolutely well with existing data. And in this particular case, we in 3D can even get a compression of 95% and get away with memory that is just 5% of what originally would be needed. So in this case, we also looked specifically at the runtime. So we implemented the standard direct numerical simulation code on a laptop. This runs on a laptop. And the kind of corresponding matrix product simulation on a laptop. And then we looked at the runtime of the two as a function of the number of qubits being used. And so basically here, 20 qubits would correspond to a 2 to the 10 times 2 to the 10 grid. This is in two spatial dimensions. So here for this kind of lid-driven cavity, we look at what we need as a chi. So the chi does hardly change with increasing the number, with increasing the fineness of the grid. The MPS calculation goes exactly like the chi to the 4 that I said before. That is limited by the multiplications that we need to do between different matrix product state. Whereas the direct numerical simulation now, of course, goes exponentially with the size of with the number of qubits, because the grid size goes exponentially with n. So basically, every time we add 2 qubits, we kind of double or we halve the grid size, and that means that direct numerical simulation is much slower. And if we compare the two kind of runtimes, we find that at around something like 20 qubits in our simple implementation, the matrix product state wins over the direct numerical simulation, and then of course takes off. So at 22 qubits, you have already a factor of 10 improvement, and at 24, it would almost be a factor of 100. And of course, this is all highly implementation dependent, so I can't make any kind of generic claims. Now, I do run out of time, I realize that. What I wanted to just say quickly is that now, of course, what we usually do in everything we do is we take a quantum system, and we rewrite it as a matrix product system, and then we try to find out about the quantum system by solving the matrix product problem. Now, of course, we can do the opposite. We here have a matrix product problem, and we can now ask the question, can we actually turn this into a quantum system, solve the quantum system, and then get the solution to the original problem that we want? And so this would basically, is basically one thing we looked at in this kind of so-called hybrid optimization, where you use a kind of feedback loop between a quantum computer and a classical computer to do this variational optimization. I don't have time to go into this in any detail, just to say that all of these kind of operations that we've been doing so far that scale like chi to the 4 are, of course, now not scaling anymore because they can be done without any limitations to chi. And everything that I showed so far will just scale polynomially, usually with a low power of the polynomial in the number of qubits that is used. So this is exponentially more efficient than doing the classical version. But of course, we do have to variationally create the trial states. So what we still have to do is we have to find variational networks that create the flow fields. And these flow fields will, of course, have a chi that increases, as I showed before. And so far, we needed to create these flow fields with operations that scale like chi to the 4. If instead you want to do, and I'm skipping through this, I want to go here. So if instead now of this complexity chi to the 4, if you create these states all with classical matrix product states, you write down corresponding quantum networks. The complexity in generating any kind of matrix product state with a certain chi can be reduced to chi squared. So what we get immediately from transferring these types of algorithms from classical to quantum computers is a quadratic speedup. So rather than everything scaling with chi to the 4, things now scale with chi squared. And of course, only logarithmically with the size of your grid. And so that's where potentially there is an advantage in these types of algorithms compared to classical. But of course, this is also one thing that may push quantum computers to become more to actually need to try harder to outcompete classical physics. This is just a quick summary because I realize I'm at the end. So basically what we've done is we started from using tensor networks to analyze CFT type problems. We have actually analyzed how this encoding works in an early paper in 2018. This then has led to new classical algorithms that we were called quantum-inspired algorithms to actual solutions. And actually for me, the interesting thing is that from day one, when we started this, we didn't outcompete, but we were competitive with kind of the same computations that you just use the existing software for doing CFT. We find, and I think this is the key, that only a logarithmic number of qubits are needed compared to the grid that you want to describe, and that there is very limited entanglement that is needed. So this kind of cutting off the top of the pyramid here is a massive saving compared to any kind of direct numerical simulation. And we have actually studied then corresponding quantum implementations, and we might get an improvement on that as well. Now, of course, I haven't been doing this alone. There are lots of people who have been involved in this, and in particular, the people here on the list. Martin Kiffner at Oxford, who is working on these problems, and particularly on the tensor network problems. Nick, who was the first author on the initial paper, is now in Pittsburgh, working with Peyman Givy, who is a rocket scientist. So they're really going full steam towards doing combustion physics on that, partly also for NASA. I'm working now with Thomas Rung, who is a ship building engineer, a kind of real aerodynamics engineer. Sergey, who we've heard before, who helped us a lot with the maths on all of these kind of tensor train decompositions. Andrew Daly is also involved in a lot of this work. He is currently trying to adapt these types of problems to some plasma physics problems. And Michael Lubash, who was actually instrumental in the initial phases of this project, who is now at Quantinuum. I tried to kind of somehow mimic the kind of logo there, but I didn't quite manage, I guess. And with that, I would like to thank you very much for your attention. And time is up.
Time is up, but I think we can take a couple of questions. Okay, Kevin?
So why in 3D did you have this worse bond dimension scaling? Did you understand that?
No, we don't fully understand that. I mean, we don't understand bond dimension scaling at all at the moment. I mean, it's something, let's put it like this, I only understand it qualitatively from this kind of, energy cascade, but quantitatively we don't understand it. We don't understand how it will actually scale with increasing Reynolds number, whether it will ever saturate or continuously go up. I mean, you did see there were some examples, I'm not sure I will be able to get back. There are some examples where it seems on these airfoil problems that that you have a certain kind of transition in the airfoil quality at the Reynolds number of about 10 to the 5 or so it was. Can I get there? See here, at around 10 to the 5, for instance, conventional airfoils suddenly have a huge change in what they do. And who knows, I mean, what happens up there in terms of these entanglement spectra, we don't know yet. We haven't really analyzed in a lot of detail how various different flows look like in this matrix product decomposition. That's all work in progress. I mean, there's still a lot to be done. Yeah.
From Sheng Xuan Lin, it seems like MPS bring advantage to solving computational fluid dynamics by separating the scale. How does this compare to the multi-grid method?
Well, so it's a separation of length scales, and there are all these multi-grid methods. So I would say that the main advantage is that in this kind of work, I do not have to bother with choosing any kind of grid. I do not need to look at the problem first and then say, well, I need a few more points here and a few are there and so on, depending on how the flow looks. And so I let the algorithm decide where to put the resources. So in the end, I would argue that adding or kind of halving or doubling the number of grid points costs me 1 or 2 qubits. So I don't really want to put any effort into choosing a kind of grid, very complicated grid, and do some kind of multi-grading whatever thing, and choose this. I just spend another 2 or 3 qubits, and then let the algorithm go and decide where to put the resources. That would be my approach. I hope it will work.
But in principle, if you every qubit you add could double your bond dimension, right?
True.
Or every
Yes.
2 qubits, I suppose. But
Yeah, but if it did that, then I would also struggle with a hand kind of built.
That's true.
So
Okay.
there's a kind of conservation of difficulty, and I rather let the computer deal with it.
Yes, there are also turbulence problems in Bose gases. So have
Yes.
you thought about adapting this to the nonlinear Schrödinger
Yeah,
equation?
we have actually the first example we ever did in this 2020 paper that I showed before is the Bose-Einstein condensate on 4 grid points on an IBM quantum computer. And yes, that's certainly one of the things we thought of at the very, very first. So essentially, we came to this through Bose condensation. There were these experiments by Zoran Hasibabic in Cambridge, and that was one of the motivations for this.